This video will cover section 9.7, which is talking about polynomial approximations of functions and Taylor and Maclaurin polynomials. So first of all, we've done a polynomial approximation of functions before. And so let's go back and see how this looks. So in number 1, we're going to use the tangent line to f of x, which is e to the x, at x equals 0 to approximate 0.1. So just to kind of show you a visual again of what's going on, since it's been a while since we've done this, I've graphed here for you the graph of e to the x and then the tangent line. So what we're doing is we're centered at x equals 0, and then I'm using that line in order to approximate what e to the 0.1 is. So if you look at e to the 0.1, you're actually pretty close to what e to the x actually is, looking at this graph. Okay, now if we zoomed in, you can see that there's going to be error there. All right, so let's go back and calculate that that tangent line so that we can then approximate at 0.1. So to find a tangent line, you need a y value, so that would be f at our x value of 0. So that would be e to the 0, which is 1. You also need a slope, so that's going to be f prime of x, which is just e to the x here. And then f prime of 0, that would be your slope, would also be 1. So when we write the equation of the tangent line, we have y minus our y value equals our slope of 1 times x minus our x value of 0. Now, if we were just writing the tangent line, that would be fine, we'd be done. But we want to use this tangent line to approximate our function. So this would be y equals x plus 1. All right, so that's the tangent line. And then I want to approximate f at 0.1, which means I want to figure out what e to the 0.1 is without using a calculator. So this is going to be approximately our tangent line evaluated at 0.1. So that's going to be 0.1 plus 1, which is 1.1. So that would be approximately e to the 0.1. All right, now, how this relates, we've done this before, and you've seen this kind of before again with like Euler's method a little bit, but this is a different way to approximate a function with better accuracy. Now, the tangent line obviously is not going to be very accurate, especially if you look at this picture. As you move away from that center there, then this is going to be hardly any approximation at all. It's going to be very, very far away from the actual graph of e to the x. But as you're really close to that center where the tangent line touches at 0, then you can have pretty close approximation, I guess. All right, so what we can do is we can actually better this approximation by making values of the second derivatives of the polynomial approximation agree at that center x equals 0. So now what this looks like, and let me go back and say that the tangent line, what we're going to now call this is called a first degree polynomial approximation. Okay, so a polynomial is obviously linear function, then quadratic, then cubic, and so on and so forth. And so a polynomial of degree 1 would be a linear polynomial. So if I use a linear polynomial to approximate a function, I'm really using the tangent line. So then if I were to go on and use now like the second derivative to approximate and create a quadratic function that modeled e to the x at that 0 point, then that would be called a second degree polynomial approximation. All right, now we can keep doing that. We can take a third derivative or a third degree polynomial approximation, fourth derivative, and so on and so forth. So where this comes from is these two separate guys came up with this polynomial definition. We have Taylor and we also have Maclaurin. Maclaurin, I believe, was actually first, and then Taylor came after that. So this is a definition of what a Taylor polynomial and a Maclaurin polynomial are. And they're exactly what the title says. They're polynomial approximations of functions. Okay. So here's how Taylor polynomial works. Actually, I'm going to look at Maclaurin first. Let's look at Maclaurin first. So here's Maclaurin, and up here is Taylor. If you have this center at 0, which we had with our e to the x, then our polynomial approximation, so we use p for a polynomial, and then we use the subscript n to say how many degrees we're using. So if we were using the tangent line, it would be p sub 1. Quadratic, p sub 2, so on and so forth. So that would be the function evaluated at 0 plus the derivative evaluated at 0 times x. Now notice that that's exactly what we found in the very first one. If we look at, here's our polynomial, so we can call that p sub 1 of x. Then f at 0, in that case that was our e to the x, e at 0 was 1, so that was that value there. And then plus the derivative evaluated at 0, which was also 1 times x. Now, if you notice, if you stop there, then we have that polynomial that we already found here. Okay, so we can keep going with that. Now, obviously, what this is going to look like is a series, because we've been talking about series. So if we keep going with kind of that pattern, what we end up with is this definition for a polynomial. So notice the second term, we have the second derivative evaluated as 0. And now instead of times x, we have times x squared. And then we have this factorial here. So it's divided by 2 factorial. So if you actually go backwards, this would really be divided by 1 factorial, which is 1. This would be divided by 0 factorial, which is also 1. So you start to see this pattern. So then the next term, you have third derivative evaluated at 0, x cubed, 3 factorial, and so on and so forth. Okay, so that's if your center is at 0. So if your center, and that's called a Maclaurin. So Maclaurin is called centered at x equals 0. Now what I mean by centered is e to the x was centered at 0. So if you look at our graph, at 0, our tangent line is touching that graph at 0. Okay, so that's what it means by centered. So what if I'm not centered at 0? Then that's where the Taylor polynomial comes in. So that's centered at some value c. And notice that the only change here is instead of x and x squared, I've got x minus my center. X minus my center, x minus my center. And instead of f prime or f double prime at 0, it's f prime or double prime evaluated at that center. Okay, so now as your degree increases, the graph of the polynomial becomes a better and better approximation of the graph of f of x. Okay, now I know this is all very new and very confusing, so let's go ahead and just kind of follow the process for number 2, and then I'll show you in the graph how that looks. All right, so it says find the 4th degree Maclaurin polynomial. All right, so 4th degree, that means we're going to find the 4th derivative. Okay, and then a Maclaurin polynomial, what that means is our center is at 0. And then for our function e to the x, and now we're going to use the 4th degree to approximate f at 0.1. We're going to see the difference from our first example. All right, so e to the x is quite easy because as you take derivatives of e to the x, it doesn't change, right? But I still want to kind of show you the process that I would do for all my other functions. So we have f of x, this is how I would start off, is e to the x. And then I would start taking the derivative. Okay, typically you can't jump straight to the 4th derivative. With e to the x you can, but I'm just showing you the process here. So the first derivative is e to the x, second derivative, e to the x, third derivative, e to the x. All right, and then the 4th derivative, now notice I've been using tick marks, but once we get to the 4th derivative, we notate it like that. That does not mean the function to the 4th power. That means the 4th derivative, so that's e to the x. Okay, the next thing in my process that I want to do is I want to, if we look at our Maclaurin polynomial definition, we have our derivatives, and then not only are they the derivatives, but they're the derivatives evaluated at whatever our center is. So we have the functions, but now we need to evaluate them. This one's easy because it's all the same. So we're going to evaluate at our center. This is Maclaurin, so our center is 0. So e to the 0 is 1, and that's going to be the same all the way down. Okay? Again, e to the x is quite easy. All right, so now what I want to do is I want to create a 4th degree Maclaurin polynomial. So we can notate it one of 2 ways. We can use a p for polynomial, or sometimes you can use an m for a Maclaurin. I'm just going to stick with the p for now. So this is p, and this is 4th degree, so p sub 4 of x. So we're defining a polynomial. Okay, so we're defining a 4th degree polynomial. All right, so the way that works is you're going to start off with f at 0. So that's our first term. F at 0 was just 1, plus f prime of 0 times x. This one right here. So that'd be 1 times x is x. Then keep going. Plus the second derivative evaluated at 0 times x squared divided by 2 factorial. So that would be 1 times x squared divided by 2 factorial. Then you're just going to keep following that pattern all the way to the fourth derivative. Okay, so what I have right there is called the fourth degree Maclaurin polynomial of e to the x. So now what they want us to do is they want us to evaluate this at point 1, because now that's going to be another approximation for e to the point 1. So then we would just plug in point 1 in for x. Now, this would be tedious, but you could calculate this without a calculator. Okay, and that's the whole point here, is we're studying functions here, and I'm teaching you how these mathematicians were able to get e to the x and things like that, and sine, cosine, natural log, without using a calculator, and exactly what's programmed into your calculator in order to calculate a good approximation of these functions. All right, so let me kind of show you in the calculator what this would look like. So I'm going to put in this polynomial into the calculator, and I'm going to see how closely that fits e to the. Okay, so what you see in blue, and you can barely see the blue anymore, but you see that blue line close to the x-axis, that was e to the x. The red line is the tangent line to e to the x at 0. Now the black is that polynomial approximation, that fourth degree Taylor polynomial. And notice that on the right side of that graph it has completely covered up e to the x. Now on the left side it's a little bit different, but you can see that, look how good of approximation that would be for e to the x if we went even just 2 spaces away from 0. And so if I were to take this to an infinite degree Taylor polynomial, then you're going to get a pretty good approximation for e to the x. Okay, so I just wanted to give you a visual of what that would look like and why we use that Taylor polynomial to approximate e to the x. Okay? Okay, so now what I'm going to do is we're going to just try this process again for a different function. So I want us to find the third degree Taylor polynomial for f of x equals cosine expanded about. So when you see that word expanded about, what that means is centered at. Okay, so I'm evaluating all my derivatives at pi over 6. So you want that center to be something that you know the actual value of. So cosine and sine, you have more options. E to the x will always be centered at 0 because that's the value that you know for e to the x. And then for natural log of x, the only value that you know the exact value of is natural log of 1, which is 0. So natural log will always be centered at 1. All right, so for cosine, however, we're going to be centered at pi over 6 for this one. So just to kind of remind you, first of all, Taylor polynomial, we're using a Taylor instead of Maclaurin because we're not centered at 0. So again, you want to kind of start off with kind of charting this out a little bit. So I'm going to start with f of x being cosine, and then I'm going to go all the way and I'm going to find my third derivative. So the derivative of cosine is negative sine. Then the second derivative is negative cosine, and then the third derivative would be at positive sine. All right, so you want to write that out, and then next you want to evaluate each of those at your center. So I'm going to evaluate f at pi over 6. Cosine of pi over 6 is root 3 over 2. F prime of pi over 6 is going to be negative sine, so that's going to be negative 1/2. The second derivative at pi over 6 would be negative root 3 over 2. And then the third derivative at pi over 6 is going to be at 1/2. All right, so now we're going to pull all that together, and we're going to follow that Taylor polynomial definition. And so looking at the Taylor polynomial definition, it's a little bit more steps than the Maclaurin. So we have f of c. So we're just going to evaluate or write down, so our polynomial, third degree, we're just going to write down that first value that we see, root 3 over 2. Then the second term is going to be f prime of c times x minus c. And notice the degree of that is 1, so first derivative goes with first degree. So that's going to be a minus 1/2 times x minus c, which is pi over 2. Now remember, we're creating a function, so it's a function in terms of x. Then the next one would be negative root 3 over 2 times x minus pi over 6 squared now. Second derivative is squared. And then you're going to divide by 2 factorial. And then the last step would be plus the third derivative times x minus pi over 6 cubed, all divided by 3 factorial. Okay, so I know it's really complicated, but that is the third degree Taylor polynomial. Now you can simplify that if you wanted to, but leave it for now. Okay, actually I'm going to stop there, and we're going to do number 4 and number 5 in class.